Yes, please. So I just want to be sure that you are in the proper room. So please double check that you are from groups A, B, C, and I. If not, please, Jan is waiting for the others and will show you the way how to get to the rooms. So if everybody is from these groups, I may ask Francesco to continue with his talk. Thank you.
Okay, thank you. So, I will try to make a very short recap of where we have interrupted in the first part. So this was the basic setting for multi-robot exploration, and we said that we are concentrating on the techniques for deciding where to go and which robot should go where. And these techniques are studied under the names of exploration strategies and coordination methods. And we have seen some exploration strategies for deciding the ranking of the possible locations in which the robot, to which the robot can go, and then we have seen some coordination methods that are based on task allocation. So now I will introduce some very famous, let's say, techniques for multi-robot exploration. The first one is this one by Burgard and others from the University of Freiburg. And in this approach, the exploration strategy and the coordination method are interestingly integrated together. So this means that the selection of the points that should be reached and the decision about which robot should go to these points is integrated together. And the algorithm is smart and is this one. So first of all, we find a set of frontiers cells, which are the candidates that we are going to evaluate. And we are computing the cost for reaching each one of these cells for each robot. So if you have one robot, this robot, you calculate the distance between this robot and all the frontier cells, and the second robot, the same, and so on. Then you initially assume that all the cells have the same utility. So have utility 1. Then at this point, you find out which is the best pair robot from the robot frontier. That is the pair that maximizes this function here, so which is the utility minus the cost for reaching that frontier. So beta is a weight in this case. So you find out the best pair, robot frontier, and at this point comes the interesting part. Because you reduce the utility of other frontiers according to the fact that they are close to the frontier that has been already assigned to a robot. So the idea is that if you assign a frontier to a robot, the other frontiers that are close to this one will have their utilities decreased because the information that you can acquire from them can be likely acquired from the frontier assigned to the robot. And so other robots, in a sense, are discouraged to reach these close frontiers. And in this way, you have a form of implicit coordination between the robots. So you avoid that more than one robot can go to the same frontier. And okay, yeah, and you continue like this until you have assigned all the robots to some frontier. This is clearly suboptimal. So this is one example. In this case, if you assign first the frontier A to robot 2, then the robot 1 has to travel a lot to reach frontier B, and an optimal allocation would be to for robot 2 to reach frontier B and for robot 1 to reach frontier A. So this is not optimal in general, but it works very well, and it has been used several times in several different applications. Okay, let me just skip this one, and then let me go back to this basic setting, and now we are looking at how this setting can be instantiated for the case that we have called information-based exploration, which means that we know where we can take measurements, but of course we don't know the results or the data that will be measured in these locations. So in the case of information-based exploration, that is usually called also exploration, we have this particular problem formulation in which we have a finite number of sensing locations that are called V, and then we assume to have some information function that, given a subset of locations A, this I of A will return how much, a measure of how much information you can get from performing sensing from these locations. And then we have a sensing cost function, so how much does it cost for performing sensing at a location. Then a traveling cost function, so how much does it cost to move from a location to another location. We also usually assume that we have a start location and a target location for each robot, and for each robot we have a cost budget. Okay, this is, as usual in this lecture, one of the possible formulations, so you can find in the literature several different variants of this basic formulation. So given all these elements, the information-based exploration problem asks for finding a collection of paths, so one path for each robot, where each path for a robot I is a path from the starting location of robot I to the target location of robot I, such that we maximize the amount of information that we can collect over all the paths. Okay, so such that the information that we can collect over all the paths is maximized, under the constraint that each path can cost at most B, which is the cost budget there. This is the basic problem of information-based exploration. In some cases, it is also called active sensing or active information gathering. In all these formulations, they are not identical, but quite similar. The important point is the online nature. So when you have active, so this means that you have an online nature of the problem. So your next step will depend on the previous steps, okay? And you cannot plan usually everything from the beginning. Okay. So in this case, what are exploration strategies? So exploration strategies are ways for drive the robots to the next candidate locations. And in this context, the best candidate locations to which robots should be directed are the most informative points, given what you know about the environment so far. So with respect to the previous problem of frontier-based exploration, in that case, what you know about the environment was pretty obvious. So you know some portion of the environment, and then you don't know what is beyond this portion of the environment that you have already discovered. And so the representation of what you know is basically a map of the environment. Let's say a typical representation is a grid map in which you have known cells that can be free cells or obstacle cells, and you have unknown cells that you have not yet sensed. Okay? So in the case of frontier-based exploration, it is easy to represent what you know about the environment. In the case of information-based exploration, this becomes more complex, and you have to find out ways for basically representing spatial and temporal phenomena. So some phenomena or some quantity that can change over space and over time. Probably the most used approach for doing this is to use these Gaussian processes that I will just, okay, it is a very long story, but I will just show you the main idea of what a Gaussian process is a stochastic process in which you have a number of random variables that are indexed in time or space, and with this property, that if you take an infinite subset of this random variable, they have a multivariate the normal distribution. So they are ways for capturing physical phenomenon happening in space, and here I show a very, very simple example with one dimension. Of course, you can have 2 or 3 dimensions. Okay, the representation just becomes more complex, but the idea is still the same. So we assume that the dotted red line, which is a sinus curve, okay, yeah, is the phenomena, and then you have some observations of this, which are the red points, and then you try to infer what is the quantities that you have not measured. So here you don't have a measure from this point, and the Gaussian process can tell you that it is something in between these interval here. So how is shaped this kind of blob here or of blob here will depend basically of the covariance function that you use for modeling the spatial correlation of the phenomena. So this is just one examples, but there are several ways for doing this. The real reason why these Gaussian processes are used for modeling this kind of phenomena is that they have this very nice property. So they can tell you not only an estimation of the values that you have not measured, but also a confidence interval over these values. So, and this is, or let's say some uncertainty over this value. And this, in application, is really, really important. So I take some measurements, okay, and I would like to estimate, not just by an interpolation, what is between these, what is the value between these two values, but I would also like to have some information about the related uncertainty, okay? And this is something that the Gaussian process can provide you. And, okay, so once you have a way for representing your measured phenomenon, then you can select the most informative points as the informative points that are maximizing some information measure. So one typical approach is to use this mutual information measure. I will explain it in 1 second. Or you can use different formulations of entropy for deciding which points are most informative. So can help you to reduce the uncertainty that you have about your phenomena the most. Okay, in general, also the problem of finding the optimal sensing path is an NP-hard problem. Okay, let me just show one approach that is very famous, also this one. This is by Singh and Krauss and Guestrin, and the approach is based, in this case, on the idea of using mutual information for deciding which are the interesting points of the environment that the robot should visit. So in this case, H is the entropy function, and then these are the random variables that are associated to measure in location V minus A, in location V minus and in location A. So basically this difference is that how much you can gain if you make some measurement in A. Okay, how much information you expect to get given your model of the phenomena if you are making some measurement in location A. And if our system has this nice property of submodularity, which means that the more location you sense, the less you will gain in sensing in a new location. So it should be pretty clear from here. So if you have a set of sensing location A and the set of sensing location B, which is larger than A, then if you take a new sensing location S, which is not in B, and so of course not in A, then if I add a new location to A, okay, if I add a new location to A, my gain will be larger than if I add the new location to B. So if I am already sensing in several locations, adding some new location in which I will make a measurement will provide me less than if I add these to a smaller set of sensing locations. So this property is sometimes called diminishing returns. So I can get less and less and less if I perceive more. And okay, when this property holds, then in this paper a very nice algorithm is proposed. It is a greedy algorithm. It is called also a sequential allocation algorithm that works like this. So let's assume that in this case all the robots should start from this point and end up here, okay? And then we plan like this. So we plan the optimal path for the first robot. Then we fix this path and we plan the optimal path for the second robot. Then we fix these two paths and we plan the optimal path for the third robot and so on. So we try planning the optimal path for each robot to add as much as possible to my information gain. And the interesting part of this is that we can have an approximation guarantee on this algorithm that is 1 plus eta, and eta is the approximation. It is the approximation guarantee of the single path planning algorithm, so of the path planning algorithm for a single robot. This is the basic algorithm. You can have more complex algorithm for for this, but okay, yeah, it's something that you can read there if you are interested. This is another similar approach in which the coordination between the robots is completely different. So in this case, this is EMAS 2013. So we assume to have an anisotropic field. So this means that the main direction of change of this field is along a single direction. Okay, so this means, for example, in this example, the main direction of change is this one. So this means that along the vertical direction, the field doesn't change too much. Okay, so if we have this kind of the situation, we can plan the informative path for two robots in this case, step by step. So we have like a first joint planning for the first step, then a joint planning for the second step, a joint planning for the third step, and so on. So we can just move one column to the right, okay, and every time we can add a single step to the plans of the two robots. Since we are planning for just one step, it is not so expensive to plan jointly for the two robots, okay? And, okay, yeah, this is the basic idea, and then you can have some efficient approaches that can improve these, like each robot will select its own best path, and then it will share the observation it obtains with the other robots. So all the robots are informed about what could be the next steps and so on. Oh yeah, there are also some other approaches for doing this. This is just a couple of them. So use of DEC PO MDPs. Do you know decentralized PO MDPs? Okay, let me just show you this. Do you know Markov decision processes, MDPs? No, okay, I will explain this. Okay, in a Markov decision process, you basically have a single agent, okay, that is acting in an environment, but it has uncertainty about the effects of its actions. So it performs an action, but it doesn't know which are the effects of this action. Actually, it knows a probability distribution over the effects. But in a basic Markov decision process, in a basic MDP, then the agent has a perfect knowledge about the state of the environment. Then we can move from a MDP to a PO-MDP, which stands for partially observable Markov decision processes. So in this case, the agent has one, uncertainty over the action, as before, plus uncertainty over the observations. So it doesn't know the state of the environment. So it has a probability distribution that relates the observation that it gets to the real state of the environment. So the agent doesn't know the real state of the environment. If you move from a single agent to multiple agents, we have this framework that is DEC, that stands for decentralized PO-MDPs. And here is the formal definition is a little bit involved, but it's not complex to understand. So this is the basic schema. You have a number of agents, okay, and you have an environment that can be in a number of states, but these states cannot be directly observed by the agents. What the agents can do is to perform some actions in the environment and receive some observations from the environment. And basically, the model is like this. So each agent has its set of action and its set of observations, and we will call A the joint action that the system as a whole can perform. And we define two basic functions, actually, that are describing the interaction with the environment. One is the transition function that says that given a state of the environment and given a joint action of the agents and given the one possible next state, it returns the probability of the possible next state. So given this, if the environment is in S and the agents jointly perform an action A, which is action A1 for agent 1, action A2 for agent 2, action A3 for agent 3, then this function will return the probability to end up in state S prime. And a similar thing happens for the observation. Okay, so given a state, given the joint action of the system, and given one possible observation, this function basically tells what is the probability of getting this observation when the world, when the environment is actually in this state here. And finally, we have this reward function that given the state of the environment and the joint action of the agent, we return a real number, which is the gain of the system in some sense. So the agent will try to act, okay, the optimal policies in this case, the agent will try to act for maximizing the sum of future rewards that they will get, okay, from the environment. So this has been exploited in the paper. I think it is ICRA or something like that, I don't remember, has been exploited for solving the planning of paths, which are sequence of actions for performing information gathering tasks. And then very recently, of course, also in this field, there is a lot of attempts of using deep learning, okay, for planning paths. This is on RAL, this is the Robotics and Automation Letters this year. And this is a work that use multi-agent deep reinforcement learning for learn how an agent can perform in a coordinated way with the other agents, it can follow its path. So basically, this is how a robot is structured. The most important part is this module here, which is agent. That is basically a reinforcement learning policy that has been learned using this deep reinforcement learning network. Okay, I will not go in the details here because it will take too much time. But the message is there are several approaches for solving this information-based exploration. So you can use several different models and several different mathematical tools for solving this problem. So one important point that I would like now to introduce is the following. So far, we have assumed that robots can communicate with each other. Okay? So what happens if they have some constraints? So I just show here a couple of these possible constraints. One of these constraints is this. So assume that we have a base station, and assume that we have the constraint that every time each robot discovers something, then there must be a connection, a multi-op connection in this case, with the base station. So the application in this case is that it is really hard sometimes for robots to recognize victims. Okay, so a good way for doing this is that you have a camera on this robot, and then you have a network connection with the base station at which a human operator is looking at the camera of the robot, and he or she is deciding if what has been found is a victim or not. okay? And in order for doing this, you have to keep a connection with the base station every time I discover something that is interesting, okay? And this is one possible constraint that is related to limited communication. And this is another problem, just to tell you that if communication is not always available, then we can have very strange situations. So let's assume now that robot A and robot B does not communicate with each other. So this is an environment is partially explored. We have two frontiers, one in red here and one in green here. But if this yellow part has been already discovered by robot B, but robot B cannot communicate with robot A, the robot A does not know that this part is already known to the system. So you can waste a lot of effort because robot A could think that it is a good idea to go there. Okay, and this is the typical situations that happens when you include communication restriction in exploration. And okay, this is a survey that we have done a couple of years ago on this. So this is just what are the possible communication models that we can use. So the basic one is line of sight. So we assume when you plan where the robots should go, we assume that they can communicate if they are in line of sight. So if we can connect them with a line segment that does not touch any obstacle. Or we can assume that they communicate if they are, and this is also quite typical, if they are inside a circle, okay? So if I have a robot, I have a circle of some radius, okay? And if another robot is inside this circle, then the two robots can communicate with each other. Or we can have more complex way to model the signal propagation in the environment. So there are simple models that are basically like this. So you take 2 points, and then you take the line segment that is connecting these 2 points, and then you count the number of walls or the number of obstacles that are along this line segment, and you apply some decay of your signal according to the number of walls that the signal encounters. And at the end, you can decide if they can communicate or not, according to the fact that the power of the signal is below or above some threshold, okay? These models are very simple, so as far as I know, there is no model available in robotics that is modeling, for example, the reflection of the signal in an environment, which is in the real world, which is the basic mechanism for which you can use your cell phone in indoor environments. So because there are reflections, okay, and these are not modeled in. There was some work by some Japanese guys some years ago, but the model was so easy to compute that it was unusable in any practical applications. And then, okay, this is how do you think two robots can communicate, and then which kind of constraints can you put on the communication? So you can impose that the robots are always connected, or that they are connected at some special times. So when they discover something, as we have just seen in the case of the victims, or after some timeout, so this is called periodic reconnection, okay? After 3 seconds, we need to reconnect, okay? We can stay disconnected, but after 3 seconds, or after 30 seconds, or after something, we have to reconnect. Okay, so yeah, this is a classification of some words. I will go fast on this. Okay. How is the communication modeled, typically? It is modeled in this way. This is something that we have just seen in the first part of the class. We assume to have two graphs. One graph is the movement graph. So it is the graph that is telling where I can move. And the second graph, the dotted lines, is called communication graph, which says from which vertices we can communicate. So this means that we can communicate if a robot is here and another robot is here, we can communicate with this from these 2 points. The models can be simple. The communication graph can be just a graph, or it can be a weighted graph. So you can also attach to the edges of the communication graph a number, which is the quality of the bandwidth of something that is related to how much information you can communicate. Okay, and okay, and you can have different different situations. So okay, you can communicate in different ways. Also here, just a couple of examples of the methods of exploration that is doing with these limitations in the communication. This is one work from 2012 and by Jeff Dollinger. And then the idea here is that you have a known environment, and then you have robots that are going around to collect some information. The communication is assumed to be line of sight, and the algorithm that they propose, actually one of the algorithms that they propose, work in this way. So we have two robots here, the red one and the green one, and so they should go to take some measurement of this black circle here, and the idea is the following. So the first robot plans, assuming that the second robot is static. So the first robot plans in order to be in line of sight communication with the second robot and at the end of the path. Okay? Then the second robot plans knowing the plan of the first robot. And then this is iterated. So the first robot plans, fix the plan of the second robot and so on until convergence, okay? And they will converge to usually smart path for collecting information and being in communication with each other at the end of this. Okay, yeah, I can just show you this other example. This is also another of our works, but I will mention it because it helps me to introduce a mathematical technique that is very commonly used on this. So in this case, we have an unknown environment. And okay, we have a base station that here is placed exactly there. Okay, we have a mobile robot that, of course, as usual in this case, have a finite range sensor, and we can assume line of sight or circle communication model. And the goal is to find at each step which poses should a robot take, so which positions should a robot reach in order to ensure two things. The first one is that the environment is explored in an efficient way, and the second one is that when a robot discovers something new, there is a connection with the base station. So this is the solving algorithm for the problem of the victim that I have illustrated at the beginning. And for solving this, as not only in this work, but in several other works, it is typical to use these integer linear programming problems, and I would just like to show you how they work in this very simple case. So no need to, understand everything here. But this is a very common technique, not just integer linear programming, but also mixed integer linear. The programming problems are very commonly used. Why? Because there are very efficient solvers. Okay, so if you can cast your problem in such a general problems, then you can exploit some solvers that have been developed by others. Okay, just to understand what we see. So we have R that is indexing the robot, V that is indexing the vertex, G of V is the information gate that can be obtained in vertex V, DRV is the travel distance between the position of robot R and the vertex V. So, and the variables that we have to set, that solving the problem means setting one value for these variables, is ZRV is 1 when robot R is assigned to vertex V. YV is 1 when vertex V is assigned at least one robot. So we say that vertex V is part of the solution. XIJ is 1 when the edge ij is part of the solution. So this means that I in vertex I and in vertex j I have assigned one robot. Okay? Okay, so if you look at the objective function, what we are trying to maximize, just forget all the details, just look on the main element. We are maximizing the difference between the information gain and the distance traveled by the robots. So what are the constraints saying? So, okay, this is saying, actually, if you look it for 5 seconds, if you're not an expert, it's not easy, but it says that the deployment that we are calculating should be connected, okay? And it has to have the root in the base station. So this means that every information can be forwarded to the base station. Then the second constraint is saying that each vertex of the solution is occupied by exactly one robot. So if you fix V, and then you sum over all the robots that have been assigned to V, this number can be 0 or 1. And this is the meaning of this variable here, which is exactly there. So this is basically the other way around, so that each robot occupies exactly one vertex in the solution. Then we should say that at least one frontier is part of the solution, so we must discover something new. And then we have some technical constraints that if some robots are not available for allocation in this round, they should keep their previous positions, okay? I assume that they stay stable. So let's see one example of this. This is a synthetic example. So this is the control center. So this is like the base station. These are the robots. We assume that the movement graph and the communication graph are the same in this case. And these are the frontier F1, F2, F3, and F4 that we would like to visit. So at first, the method can say, okay, I will allocate robot R2 to R3, sorry, to frontier F1, robot R4 to frontier F4, and robot R1 and R2, they are allocated to these two vertices just to compose this continuous connection with the base station. Okay? So then the robot starts to move. We assume that these three robots, 1, 2, and 3, have reached their position, and the robot 4 is still traveling to frontier F4. While it is still traveling, we can move the other robots, and the system allows to do this as far as we keep the connection of the tree with the at the base station. And this is something that actually works, okay? And, okay, yeah, this is some video, but I can skip it because I would like to show you the next part and the final part of this, that is multi-robot patrolling. So this is the third canonical task. So we have seen coverage, we have seen exploration, and now we are looking at the patrolling, which is a very, very particular case of information gathering in which we try to collect information from the environment about other agents that can make some decisions, not about some phenomena that happens in the world, but about other agents. So this is the problem formulation. So we have a space that is known to the robots. We have M mobile robots that are moving in the environment with some sensing tools. And then we have one or more targets if they have neutral behavior, or adversaries if they have an opponent behavior. So if they act against me, okay, in some sense. The patrolling problem asks for finding paths for the robot in general, such that when the mobile robot will follow this path, then the targets or the adversaries are detected or are captured. So the end of the game can be just to see the target or to see the opponent or to capture it, just to maybe enclose it in a circle or doing something like that. The problem can be approached online or offline according to the knowledge that we have about the target and about the behavior of the opponent. And basically we have several formulations. So one is frequency-based. So just repeat coverage with some guarantees over the time that it will take to pass over the same point. So it's a problem of repeated coverage. Or it can be formulated as a problem of adversarial patrolling. So that is resorting to techniques of game theory. Okay? Okay. Yeah, and the end of the game, as I said, can be the detection of the capture of the opponent. We can, in some cases, guarantee that we can detect or capture the opponent, or in general, we can maximize the probability of detecting, of capturing this. So a solution in this case is basically a joint strategy or a joint policy, one policy for each robot, that can be revised at each time step according to what I know that is collected in this MT, okay? According to what I know about the behavior according to what I have observed about what the opponent can do. And the optimal solution tries to do this as efficiently as possible, and these are some measures that are used for measuring efficiency. So the shortest time, the shortest traveled distance, the minimum energy consumption, and so on. Usually, if you compute an offline solution, so you are assuming a worst case stance. So you are assuming the strongest opponent possible, okay? And then you can calculate an offline solution with some guarantees. So just to show you one example of this is by Noah Agmon, Journal of Artificial Intelligence, JAIR, 2012, okay? Is a very simple model in which you have a closed perimeter, so a fence, and you have to patrol this fence using M robots. So the idea is that you take the fence, you segment it in M segments, okay? And then you assign a robot to each one of these segments. So each robot is assigned to one segment. And the robots have a very simple behavior. So they can move forward with probability P, and they can go back with probability 1 minus P. Okay, so at every time step, they will decide if they will continue or they will turn back. In both cases, they will always stay in their assigned segments. Okay, so if they are at the extreme of the segment, they will for sure come back. So the paths that result from this approach are probabilistic. So okay, it's like a random path. The attacker is adversarial, and it is assumed to have full knowledge of the behavior of the robot. So it is, and this is the typical worst case assumption. So we assume that the attacker has observed my robot for such a long time that it knows the probability P with which they change direction. So this is tricky. The attacker knows the strategy of my robot, but of course, being the strategies of the robot probabilistic, the attacker does not know the realization of these strategies. Okay? And the point is that to find out this probability P such that we are maximizing the probability of penetration detection. So to detect the adversary that is penetrating along any one of these segments here. Okay, and this is something that can be done. Okay, so sorry, I will skip some parts and then okay, yeah, okay, and time is running, and so I come to some conclusions. Okay. So, just to conclude what we have seen. So, you can see more examples of the techniques on the slides that you have available. So, the problem of planning coordinated path for multi-robot systems employed in information gathering tasks can be formulated, and I think that this is clear from this discussion, can be formulated under different names, and actually not under different names, but under different canonical tasks. So we have really several tasks that are coverage, exploration, patrolling, of course that there are also other tasks, okay? But you can, they are different in their nature, in their basic assumptions, okay? So they are different tasks. And one point is that there is no any unified model for solving each one of these tasks, and moreover, there is no any unified model for solving the information gathering task. So what you use for information-based exploration is usually not a good technique for patrolling, because you don't consider explicitly the presence of an adversary, okay? And so there is no any global technique or any general technique that can be used in all these situations here. And so what is a good approach for developing a decision-making method for multi-robot systems employed in information gathering tasks? So this is my suggestion and my approach. So you start from knowing an application, and then after you have studied an application, you can come up with which capabilities you need your robots to exhibit for solving these or for addressing this application here. So it is a problem of coverage, it's a problem of frontier-based exploration, it's a problem of target tracking, it's a problem of what? Then, when you have these, then you can look at algorithms that have already developed, or families of algorithms that have already developed for this kind of canonical tasks. So if you are a problem of coverage, is it a good idea to use cluster the clustering the point plus the SP, to use a spanning tree, to use something else, okay? And then, finally, you come back, you go back to the technologies like ROS, but this is the bad part. So you will hardly find some of the techniques that we have discussed ready for use. You are, in most cases, you need to re-implement it for your specific, oh wow, it's time to finish? Okay, for your specific application. So these are some of the software tools that have been already discussed also yesterday that you can use in this field. So I just add that there are a lot of resources about ROS and Gazebo for multi-robot systems in the RoboCup virtual robot competition. So there are some links where you can find something about this. One interesting part is this one, is the wireless communication server. So one of the most important part is that if you are using ROS for the multi-robot systems, you don't have any native way to implement the effect that there is no communication between two robots. Okay, so you have to add something. Okay, and this is the solution with which the guys, I have participated for some years in the virtual robot competition. We come up with the solution here, which is basically a ROS node that is managing the possibility of connecting between multiple robots. And then there is, for very quick prototyping, this multi-robot exploration the simulator. This is done by a group at the University of Oxford, and it is written in Java. Is physically, it has no any physical simulation, but it has some simulation of the communication between the robots, and it is, especially for students, is really a good tool for quick prototyping of solutions that of course then you have to test in more complex environments. So I ran a little bit late, but I think that that's all. So thank you very much.
Thank you for the presentation, and we have some time for questions. So do you have some questions? So I will start here because it's closer and then continue.
So thank you. Thanks for the presentation. You mentioned 3 canonical tasks, which is coverage, exploration, and patroning. I also noticed that there are many papers working on multi-robot, surveillance, monitoring. So do you think there is a difference between those terms and the tasks you mentioned?
Yeah, I would say that often monitoring is like what I've called here in this presentation here, information-based exploration. So because usually you know where you have to go, but you don't know which are the measurements that you are going to perform. So you know the lake, okay, like in this case, but you don't know which are the concentration of something or the temperature of something in the lake. So this could be a case of information-based exploration. But I agree that the names are there are a lot of names for calling the same thing. Here I had to make some choice because otherwise we cannot understand each other, but I'm not claiming that my names are general or are the only possibility for calling something.
Okay, thanks.
Yeah.
I have two questions. First is that in one of your constraints, there is a, you said in one vertex there should be no more than one agent allocated. So I was wondering if this would maybe block a more better trajectory that has a cross point between two agents. So
Sorry, I cannot hear. Sorry. Can you speak louder, please? Not two agents can be in the same vertex. Is it this question? No.
No, in one vertex, there should be only one agent allocated in the trajectory.
Okay.
In one of your constraints. So does that mean the another agent cannot pass that point? They cannot go through the point. That means maybe it's blocking one of the best trajectories. So is it?
No. Okay. It depends. You can have some such constraints. So there are typical in 2D environments. So if I have a 2D environment and if I have a cell with a robot there, so another ground robot cannot pass on that cell. But if you have, let's say, UAVs in a 3D setting, then it is quite possible to have more than one robot at the same cell. But this is usually something that you can, it is not something that is fundamental for the models. It's just some constraints that you can add to the kind of the solution that you are looking for. But it is not a constitutive part of the model. So it's something that you can add or not, but it doesn't change the nature of the problem.
Another question is that I was wondering how do you get the information function, because in practice you actually have to get to the point that so that you can have the information functions at every point of the map. Is that true?
Yeah, okay. To solve the task, yes, actually not in every point. It depends on the task. But in deciding where the robots are going, the method usually estimate how much information can be obtained from a point, and this can be done in different ways.
So you can estimate the information that you can get before you plan the trajectory. Is that?
Yeah. One typical possibility is that, for example, in frontier-based exploration, is that I have a frontier, okay, and I try to put there the footprint of my sensor. Okay, and I look at how many unknown cells I can cover from there. Of course, this is an optimistic estimate, because I don't know if there is a wall just 1 meter beyond the frontier, but this is something that is usually employed.
Thank you.
Excuse me, I have a question. Thanks for the interesting talk. Regarding the active sensing, if we consider a dynamic environment, so could we still prove the submodularity?
Sorry,
Okay,
I cannot really hear.
I'm
Sorry.
Okay, I'm saying regarding the active sensing that you were mentioning, if we consider a dynamic environment, could we still prove the submodularity or no? No.
Sorry, I cannot hear. I have really big problems, sorry.
Can you hear? Okay, so...
No.
I'm saying the active sensing.
Okay.
So if we consider a dynamic environment, could we still prove the submodularity or no?
Yeah, the environment can change, okay, and in the case of active sensing, this is question of how to set the termination condition. So if I need just one pass over the environment, or if I need something more, and in some cases it can be let's say a never-ending task. So I can continue monitoring because if the environment is continuously changing, so I cannot reach any stationary conditions. So if I know that at some point the environment will be stationary, then I can set the termination condition according to some value of the entropy. So when I cannot decrease the entropy more than something, okay, I have a good model of the environment. But I have to know that it reaches some stable state at some point.
Yeah, thank you so much for your talk. I'm not sure how much this question relates to your talk, but I was curious regarding the communication between vehicles. In your talk, when you said there's no communication, that basically meant between any two vertices there might be no communication. Have you ever looked into when just there is none at all, but there is, depending on the choice that the robot makes, that will disturb the environment, and that disturbance can be felt by the other robot? Like, I'm not, like, again, I'm not sure how much it applies, but I was just curious.
Okay. Okay. I have presented some basic form of the communications between robots. There are some works that are considering this kind of a situation in which robots are not communicating with each other, like with Wi-Fi or something like that, but they are using the so-called traces. So they just put something in the environment or change the state of something that is already there, and then another robot goes there, and then it can detect that something has been changed by another robot. There are a lot of works, of course, apart the works in Swarm, okay, but there are some works on this by Elizabeth Jensen and Ede Maria Gini from University of Minnesota. So they are using this kind of approach for exploring environments with a fully decentralized system. Yeah.
Another question? If not, thank you for your first job, or second even.
Thank you.
Yep. So, yeah, now we have the lab tour for you, which means that I will ask you to follow my colleagues. They will split you into 3 groups, so roughly 15, 16 people. So just continue through the doors, and after you are 16, we will make another group. So let's try to organize it somehow. So just you can just simply follow us. It will take 1 hour we will take you around, and then there will be a coffee break, and you will go back to this room for short presentation. So you can leave your stuff here. I think it's quite safe. Or my laptop is here all the week.